All right, we know that we can consider a definite integral to be the area, the net area under a curve or between the curve and the x-axis over an interval, right? But we needed a good notation just to express the operation of anti-differentiation. And since we found that taking an integral is really just anti-differentiating and plugging in the endpoints, we decided we would just use the integral as that symbol that indicates, hey, I want to find an antiderivative. So if I do an integral symbol with no endpoints, that's exactly what it's mean, and it's just called an indefinite integral. An indefinite integral. So the integral of lowercase f of x dx equals uppercase f of x means that if I take the derivative of uppercase f, I get back to lowercase f. And I've already, like I said, been kind of using that notation. One thing you have to understand, though, is actually when you take an antiderivative, you don't get back a single function, you get back a family of functions. Because I could do, again, what's the integral of x squared dx? Yeah, 1/3 x cubed, or x cubed over 3, right? But couldn't you also say that it's x cubed over 3 plus 10? When I take the derivative of this, do I still get back to here? Or I could say plus 100, or plus 1,000, or 10,000. You get the point, right? So literally plus any constant, right, will work. Because the derivative of a constant is what? 0. So to indicate the actual solution, which is a family of functions, I would say that the true general antiderivative is x cubed over 3 plus c, where c can be any constant. Does that make sense? We call that the constant of integration. You only need that constant when you're dealing with an indefinite integral. A definite integral is an area. It's a number. But an indefinite integral, you have to add that plus c, that constant of integration. Questions about that? Everybody feel okay so far? Anybody crying yet? All right. Here's a big old table of antiderivatives. So a couple of things that I'll note for you. The integral of a constant is that constant times x plus c. This is the power rule for antiderivatives that we developed together. A couple of other interesting ones. We know that the derivative of e to the x is e to the x, so that means the integral of e to the x is also e to the x, right? One interesting one, the integral of 1 over x. You cannot use the power rule on that because that would get you x to the 0 over 0, right? So we have to think of a function whose derivative is 1 over x. Well, that function is natural log, right? The derivative of natural log is 1 over x. However, in this case, when we're going the other direction, when we're integrating 1 over x, we have negative values in the domain of this x. It's okay to have like 1 over a negative number, right? 1 over -2, 1 over -3. But natural log is only defined from 0 to infinity. So when we take the antiderivative of this, since negative numbers are in the domain of this function, but they can't be in the domain of this function, it's actually natural log of the absolute value of x to make sure all the inputs are positive.
Because like, okay, so you had like, if you were looking at natural log, and you were just given that 1 over x, and then we added 1 to it, that'd be 0
Yeah,
and then put that over.
doesn't work. Over 0, undefined.
That's how we know that.
Right. This is basically how we know. It's just you can get in habits of going, oh, it's x to a power, so I can just use the power rule for antiderivatives. That's true for every number except x to the negative 1, right? All right, and then a few others that you're going to need. So, as always, this is up on Canvas as a PDF, and you can just access it there. You'll do enough of these that you'll be able to recall some of these, but you might, if you have a smartphone, everybody has a smartphone, right? Nobody's using like a razor. If you just go to your app store and do AP Calculus AB flashcards, you can get flashcards because while everything's pretty much open note for the rest of the year in my class, the AP exam clearly will not be, so you'll want to have some of these just basic derivatives and antiderivatives committed to memory. Like I said, you'll do enough problems where you'll get them relatively committed, but you don't want to have to go like searching through your brain for a long time. You want these to be pretty natural when you're taking the exam so you can focus more of your energy on the actual calculus of the problem. All right. Oh, other thing, you don't need, this is called hyperbolic trig, and we don't need those. So those ones on the very bottom are unnecessary. All right. So there's one other rule for anti-differentiation that you're going to need, and that's called the substitution rule. So there's kind of a hierarchy of techniques, right? Let's say I give you an integral problem. You look at it. First thing, can you just do it by inspection? So that's like if I give you the integral of cosine. You go, okay, what the derivative of what gives me cosine? Oh, sine, so the antiderivative must be sine. 2, can you just use the power rule? Is it just a bunch of variable terms to different powers? 3, if neither of one of those is the case, like the first one we did, oh no, you know what? We did like 29 from the notes, and that was like the integral from of x minus 1 over root x. Okay, we can't just do that by inspection. I can't just apply the power rule. So can you simplify the integrand and then either do it by inspection or use the power rule? And that's what we did here, right? And then last, if you've exhausted all of those, it's probably substitution. So like here, I can't do this by inspection. Do you guys know a function that if you took the derivative would give you that off the top of your head? Yeah, got it memorized. There's nothing to simplify. So then I go, okay, well, probably a substitution. And so when we do a substitution, it's called a U-sub. The idea is that we're going to define U in such a way that it's in terms of x, and we can simplify the integral, replace the differential with du, and it gives us a new integral that's now in terms of u du, but that's easier to deal with. Then you can integrate it, and then you can do a reverse substitution at the end. Sounds complicated, it's not that bad. But it'll take a little bit of practice. So, all right, how do you decide on what u is? You're trying to get a simpler integral, and oftentimes this is basically the reverse chain rule that we're doing here. So, what you want to do, rule of thumb, if there's an inside function, try and let u equal that. One thing you'll never do is let u equal x. That doesn't do any good. You're just going to rewrite everything the exact same way, but with u's instead of x's, okay? So in this case, there is an inside function. It's 1 plus x squared. So let's try that. So if I let u equal 1 plus x squared, my goal by the time this is done is to have only u's, and importantly, to have my differential be in terms of u, because that's the thing that tells me what's my variable. All right, then du dx, meaning the derivative of u with respect to x. If u is 1 plus x squared, what is the derivative of this function with respect to x? It's 2x, right? So now I'm going to separate this Leibniz notation. I'm going to treat the numerator and denominator as they are, as a numerator and denominator. I'm going to multiply dx to the other side. So multiply by dx, dx. All right, so that gets me du is equal to 2x dx, right? All right, so now let's look back at our problem. What are we going to be replacing this 1 plus x squared with? What's that going to become? U. And I said we also need to replace everything else, including, importantly, the differential. Well, notice that we have du equals 2x dx. Do we have 2x dx left over right now? We got 2x, we got dx. What's that going to become? Du. Awesome. So now my integral is this. The integral of 2x dx got replaced with du. What's under the square root gets replaced with u, and everything's accounted for. So now I'm just looking at the integral of root u du, right? This color doesn't really read very well on the board. Everybody see that? You're allowed to interact. All right. Now I don't just know this by inspection. Can I use the power rule on this one? Yeah, I just need to rewrite it as e to the 1/2, right? And what's the antiderivative? Two-thirds u to the 3/2, right? Add 1 to the exponent, divide by that new exponent. Now, this was an indefinite integral, so what can I not forget? Plus c, plus a constant, right? Great. Also, I asked for an integral of a function that's in terms of x, and my answer is now in terms of u. I don't want that. So now we go back and reverse the substitution at the end. What does u equal? So this becomes 2/3 times 1 plus x squared to the 3/2 plus c. And you could always check that answer. You could take the derivative and show that we'd get right back to what we started with, right? What rule are you going to have to use to differentiate that? Chain rule, right? So you would bring the 3/2 down, and that's going to cancel out with the 2/3, right? You would subtract 1 off the exponent. Well, what's 3/2 minus 1? 1/2. That gets me this piece, right? And then you multiply by the derivative of the inner function. What's the derivative of 1 plus x squared? 2x, and that gets me that piece right there, right? All right, that's u sub. Let's just do a little more practice with it. I don't find this one like particularly helpful because it just kind of looks complex. I would say all you want to think of this as exactly what we did last time. You're going to define u. You're going to take the derivative of u. You're going to separate the differentials. And you just need to make sure that when you start substituting, you've accounted for every part of the integral. Write that one down. Integral x cubed plus cosine of x to the 4th plus 2 dx. as you do more of these, you'll start to kind of recognize pretty quickly what you want to try and let u equal. And you're always going to be taking the derivative of whatever you let u equal, and you need some form of that to be left over to substitute out with du. So here's what I mean by that. Anybody take a guess at what we're going to let u equal in this case? Let u equal x to the fourth plus 2. Whoops. And then you know when you take the derivative of that, you're going to end up with x cubed in some form, right? And we do have that x cubed out front that'll help us substitute out for the du. All right, so now let's take the derivative. Du dx is what? 4x cubed. Separate the differentials. Multiply the dx to the other side. So du is 4x cubed dx. Now, when I actually do my substitution, let's make sure we account for everything. This, x to the fourth plus 2, I'm replacing with what? U. But I need to get the dx and the x cubed out of there. Do I have that? I do, but I'm heavy a factor of 4, right? That's fine. It's okay if there's just a constant multiple that's the difference. Move the 4 to be over with the du, meaning I'm going to divide both sides by 4. I'm going to get a fourth du equals x cubed dx. So now I just have to bring with me a constant multiple of 1/4 when I make my substitution. All right, so x cubed dx gets replaced with a fourth du. Let's start there. 1/4. That's a constant multiple, so it's okay to just factor out of the integral. Du. All right, so that was me dealing with the x cubed, the dx, right? Then x to the fourth plus 2 just gets replaced with u, so that's cosine of u. And now I've accounted for everything, right? Okay, antiderivative of cosine is sine. This is 1/4 sine u. Yes. Just based off of this equation, x cubed dx is a fourth du. So I just substituted out based on that equation. So this x, I didn't take them out. I was just trying to say, I was trying to show you guys what I was dealing with. So x cubed dx got replaced with the 1/4 du. So that's this. Because they're equivalent, right? So I replaced those two pieces with this 1/4 du. And then this gets replaced with u. So I have 1/4 cosine of u du. What do I want to not forget since this is indefinite? Yes. Plus c. Finally, we want our answer back in terms of x. 1/4 sine instead of u, x to the fourth plus 2, and then plus c. So we were dealing with indefinite integrals. You know you want to add the plus c to your answer for indefinite integrals, but what about definite integrals along with the u substitution rule? I'm skipping this slide. I know it's going to make you uncomfortable, some of you. I'm happy to go back to it. I want to give you an intuition first for how to deal with it. Graphically, we can think of a definite integral as what? Area. Meaning this is just a number. It equals some number. Do you guys agree with that? It's just like a very fancy way of writing a constant, huh? All right. When you do u substitution, what we're going to do is create this in terms of u to simplify it. But once you get in terms of u, you can update your limits of integration to also be in terms of u. And you'll have another definite integral that's equivalent to this definite integral. In that case, we don't have to do that last step of going back to terms of x. You can just keep everything in terms of u. Let me show you what I mean. What guesses on what I'm going to let u equal? That's a good start. So then what's du dx? Careful. What's the derivative of 2x plus 1? Just 2. Just 2. So du dx equals 2. Let's multiply over the dx. Du equals 2 dx. All right, so this is going to get subbed out for u, right? Do I have 2 dx? No, but that's okay because all that is a constant multiple. So I'm just going to divide the 2 over and say half du is equal to dx, right? So my integral is going to become, first thing, we substitute out the dx with half du, but the half is a constant multiple that I'm allowed to just pull out of the integral. And then what's under the radical got replaced with u, so it's just root u du. So here's what's nice about the definite integrals is, like I said, we're creating a new definite integral that's equivalent, meaning we're not going to have to go back to terms of x. But to do that, you have to update your limits of integration. Those limits, 0 and 4, are for when our variable is x. I want my limits to be for when my variable is u. So what I do is use this definition. Those variables, again, are in terms of x. So what I'm going to do is replace x with those. So I'm going to say when x is 0, u equals 2 times 0 plus 1, which is 1, right? So when x is 0, my lower limit for the integral in terms of u should be 1. When x is 4, u equals 2 times 4 plus 1, or 9. So my upper limit of integration is 9. So what I've stated here, I have an equivalent definite integral. And a definite integral is just a number. So basically, I've created a new way to come up with the same number. So now we just don't have to go back to terms of x at all. We can completely ignore this. Just evaluate that new integral like you normally would. All right. So first thing I would do is rewrite root u as u to the 1/2, 1 to 9 du. All right, do we have this one memorized yet? What's the antiderivative of u to the 1/2? Yeah, it's 2/3 u to the 3/2. Now this one is definite, so we don't need that constant of integration. Instead, we need to evaluate it at the endpoints from 1 to 9, right? So it's going to be 2/3 times 1 to the 3/2. Nope, nope, nope. I plugged in the bottom one first. 2/3 times 9 to the 3/2 minus 2/3 times 1 to the 3/2. I don't know. I think I can do this one. What's 9 to the 3/2? What's the square root of 9? And then cube that. And then times 2/3. No. What's 27 divided by 3? And then times 2? Good, so we get 18 minus 2/3. I guess that's 54 over 3 minus 2 over 3. That's 52 over 3. Right? 18 times 3 is 54. 18, 36, 54. Go ahead. Oh, no, you do. Thanks, guys. I didn't catch this. I forgot about this 1/2 up front. So I should have 1/2 times this. So I should have 1/2 times this. So that's going to be 26 over 3. Good catch. All right. I'm going to mention this because I guess it is kind of useful. If you know that a function is even, that means it's symmetric across the y-axis, right? So oftentimes it's easier to integrate. Like if I was doing the integral from -2 to 2 of x squared dx. X squared is definitely an even function. That's a parabola, right? And I'm going from these even numbers across the x-axis. So that's like from here to here. So it's just going to be 2 times this area, isn't it? Since it's symmetric. So what I can do is just update that to be 2 times the integral from 0 to 2 of x squared dx. And it may not seem like a lot, but sometimes having that lower limit be 0. 0 is an easy number to plug in, right? Because it just cancels everything out. It just makes things a little bit easier. So know that you have that option if you know the function is even. Likewise, a function is odd when it has symmetry across the origin. That is to say, f of negative x equals negative f of x. So an odd function looks like this. So an odd function is going to have the same amount of area below the x-axis as it is above the x-axis. So they cancel and it's 0. That's really useful when you're dealing with a really nasty function like this. You guys know what that looks like off the top of your head? No. But we can show that since when I plug in a negative x for tangent, tangent is odd. So it would satisfy this. So knowing that it's an odd function and I'm taking it from -1 to 1, I can right away just say that it's going to be 0. So it can be useful there. Go. Okay. Odd functions, and again, I don't find this to be hyper important. It's just like a trick you can use if you can recognize a function is odd. So one way you might do that is if you pop this into your calculator. Okay, or Desmos, and you can see that it's symmetric about the origin. Then right away, you don't even have to do calculus. You know it's going to come out to 0. So you can test this. You can either graph it or you can test to see if this is true. If plugging in a negative x gives you the opposite output. It's a good idea. Yeah, and all that really, you don't have to do this. You could just evaluate it the way we have been and evaluate it from -2 to 2 in your calculator. This just makes it easier because 0 is an easier value to plug in, right? All right, let's do one more multiple choice style problem with what we learned today. All right, so write this one down. This one says the integral from 0 to k of x over x squared plus 4 equals half natural log of 4, and they want us to solve for k. So this involves almost everything we talked about other than indefinite integrals, but all the tricks of u sub are going to be used here. The k is the upper limit of integration. It's here. All right. So it may feel like, oh, they give us the answer, so I don't really have to do the calculus, but you would be wrong. Since k is the upper limit of integration, we need to actually evaluate this integral by hand, and then we'll set it equal to that, and we should be able to solve for k. So looking at this, do you know the antiderivative of that off the top of your head? Can we simplify it at all, algebraically? You can't. You're thinking of maybe difference of squares, but this is a sum of squares, so there's no way to factor that. So no? All right, u sub it is. So what are we going to let u equal? I think that's good, Maisie. Let's try that. X squared plus 4. Then what's the derivative? Du dx. It's 2x. Multiply over the dx, we got 2x dx. Do we have that left over? So we're replacing just the denominator with u. What do we have left over? We have x dx, right? So then I just want to divide the 2 over to be with du, so half du equals x dx. Now we're ready to make our substitution, which is going to be the integral. I'll deal with the limits in a moment, but I have that half, and then x dx gets replaced with du. And then the denominator just gets replaced with u, so that's going to be 1 over u. All right, something you should know that really throws students off the first time they see it. Sometimes they'll write a problem like this as half integral du over u. The same thing. They just multiplied the du to be in the numerator there. The same exact thing. All right. Let's deal with my limits of integration. This is a definite integral, so what we want to do is update the limits to be in terms of u. So let's look at the lower limit first. When x is 0, u, using this formula that we defined for u is just 0 squared plus 4, or 4. Does that make sense? My new lower limit is 4. When x is k, what's u? K squared plus 4. My new upper limit is k squared plus 4. All right. What is the antiderivative of 1 over u? Yes. Natural log absolute value of u. So I have 1/2. Natural log absolute value of u from 4 to k squared plus 4. So I have 1/2 times natural log of k squared plus 4 minus half natural log of 4, right? All right, so that's when I evaluate the integral. Now that has to equal half natural log of 4, right? All right. Well, if I add this to both sides, I just have that natural log k squared plus 4 equals, those cancel, and on the right-hand side, I'm just going to have natural log 4, right? All right, well, we can then just drop the natural logs, can't we? Right? If natural log of A equals natural log of B, isn't it true that A has to equal B? So then I get x squared plus 4 equals 4. What is x going to have to be? Or I should say k squared plus 4 equals 4. Sorry. Oh, I forgot the 1/2 there. Apologies. I did it again, Olivia. There was a 1/2 in front of this one. All right, that's going to help. So we have another property of logarithms that says I'm allowed to bring a coefficient around as an exponent on the argument, right? So I can bring that 1/2 up as the exponent on the k squared plus 4. And so what that does for me is it gives me, here we go, k squared plus 4 to the 1/2 equals 4. This will be better. So now, square both sides, running out of space. But I get k squared plus 4 equals 16. K squared equals 12. K is rad 12. D. Yes. You could do that, but then you would have a 2 coefficient here, and before you can set the arguments equal, the coefficients would have to be the same. So you'd still have to bring the 2 up as the exponent on the 4, and you would still end up with k squared equals 6, or k squared plus 4 equals 16. Well, if you want to use this property, so the reason you have to do that is because if I want to use the property that natural log A equals natural log B, then A equals B, you can't have different coefficients. So it wouldn't be like natural log A equals 2 natural log B implies that A equals B. Does that make sense? They have to have the exact same coefficients. All right. So let's go over what we got. We got a problem set